In this section, we're going to discuss the algebraic method for determining rate laws. I've previewed this for you a little bit in the previous section, but in the previous section, the experimental data was a pretty straightforward pattern of doubling or tripling to see what happened. But sometimes the experimental data is not quite so straightforward. When this happens, it's necessary to use an algebraic method to find the rate law. Using the data, a series of equations can be set up. Each equation will have two or more unknowns, the rate constant, and the order of each reactant. However, since more than one equation can be written from the data, we have a system of equations which allows us to solve for multiple unknowns. Given the equation for the decomposition of ammonia, NH3, shown below, we will now find the rate law and the value for the rate constant using the data in the table. So we have this decomposition, 2NH3 decomposes into N2 and 3H2. We have 3 experiments with initial concentrations and initial rates. But there's no clear pattern here. I'm not directly doubling or tripling or anything. So the algebraic method must be used to determine the rate law. Okay, so I've highlighted in this light blue 2 experiments. And I know that the general form of the rate law is the rate is equal to K times the concentration of NH3 to some power M, the order that we don't know yet. And so I've chosen the 2 experiments and I've substituted the data in. So 8.0 times 10 to the minus 5 molarity per minute is equal to K times 0.0044 molarity or molar to the M power. So that's experiment 1. And then I did the same thing. I wrote a second equation for experiment 2. 0.0034 is the concentration. 4.8 times 10 to the minus 5 is the initial rate. All right, so I've just taken the 2 equations from the previous slide and I'm dividing one equation by the other, placing the higher values in the numerator, canceling out K, and then solving. So I put my first equation with the larger value for the rate and concentration on the top and the smaller on the bottom. Now when I divide the left here, 8.0 times 10 to the minus 5 by 4.8 times 10 to the minus 5, I get 1.67. The K's cancel. If I divide 0.0044 by 0.0034, I get 1.29 and then raised to the exponent M. Now, there's a straightforward sentence here that says, since 1.29 squared is equal to 1.67, if I square this, I get 1.67, M must equal 2, which is great, but the only way to do that is to just sort of guess and check, right? M obviously isn't 1, so then you try 2, and then you try 3, and then you try 4, and so on, right? You can certainly do that. And that will probably get you where you need to be most of the time. But I'm going to show you, it's sort of an intermediate algebra problem. To solve this, should you want to know how to solve for this exponent in the event that you maybe don't know how. Whoops, that's the wrong thing. In the event that you don't know how, or you just need a little intermediate algebra refresher. So 1.67 is equal to 1.29 to the power of M, right? So I just took this and moved it here. And we're trying to solve for this exponent M. All right? Now, in order to do this, we need something called the natural log. Okay? So what you do is you use the natural log. You take the natural log of both sides. So I'm also going to do it on the right-hand side. Okay, now what is the result of that? The result of that is to move this exponent into the front as a coefficient. So it's the natural log of 1.67 is equal to M times the natural log of 1.29. Okay? And now solving for M is pretty straightforward. M is equal to the natural log of 1.67 divided by the natural log of 1.29. And there's a button on your scientific calculator that says ln. And so you can just type in directly ln of 1.67 divided by ln of 1.29. And when you do that, you get a value of 2. Okay, so you can certainly use the guess and check method to figure out your m in these irregular situations. But in case you wanted to see the algebra shown so that you could do it on your own with a calculator, I've demonstrated it for you. So in this case, for this reactant NH3, this reaction rate is second order with respect to the NH3. All right, so just continuing this example, I'm going to write the rate law using the value that we found for m. On the previous slide, we found that m was 2. So I know that the rate is equal to K times the concentration of NH3 squared. Once I have the rate law and experimental data, I can find the value of the rate constant K. So I've just divided by NH3 concentration squared to say that K is equal to the rate divided by the concentration of NH3 squared. And then pick any experiment. I've gone with experiment 1 here to substitute the values for the rate. 8 times 10 to the minus 5 molarity per minute divided by the concentration 0.0044 molarity squared. And just plug in the values to a calculator, get 4.1. This is molarity to the minus 1, minutes to the minus 1. And we'll talk a little bit more about the units for rate constants on the next slide, but I just want to zoom in here and just make sure we're seeing what's going on unit-wise. On the top of this fraction, I have molarity per minute. On the bottom of the fraction, I have molarity squared. Okay, now if I were to write this also as a fraction, this would be over 1, right? So if I wanted to simplify this, it would be molarity per minute. If I wanted to see this a little more clearly, it would be multiplied by. So I change this division to multiplication, and I flip this. It would be 1 over molarity squared. So this 1 molarity cancels, and I'm left with, run out of room here a little bit, 1 over minutes times molarity. Okay, so in the bottom of the fraction, we have a positive exponent if I have 1 over minutes times molarity. If I want to flip it to the top of the fraction, I just give it a negative exponent. So that's why we have molarity to the minus 1, minutes to the minus 1. So that's where that comes from, if you're wondering. And again, we'll talk more about these units for the value of K, the rate constant, on the next slide. Units of the rate constant. The units of the rate constant depend on the order of the overall reaction. They can always be determined through dimensional analysis or remembered from the table on the following slide. So if we have a generic rate law where rate is equal to K times the concentration of A raised to its order M times the concentration of B raised to its order N. Solving for K, I just divide both sides by A to the power M, B to the power N, which is why I now have these negative exponents for inverses. So if I retain just the units here, for rate, I have molarity per second. For concentration of A, I have molarity raised to some power minus M. That's a number. There's no unit. And then B has units of molarity raised to some power minus N. Again, that's just a number. No units there. So solving for the units of K, generically, I get molarity to the power of 1 minus whatever the coefficient M is, minus the coefficient N, seconds to the minus 1. The dimension of time will not depend on the order of the reaction. It's always per second. The dimension of molarity will be 1 minus the overall order of the reaction, M plus N. The units of the rate constant depend on the order of the overall reaction. Rate constant units can always be determined algebraically. However, it is good to be familiar with the units for 0, first, and second order reaction. So I have listed the rate constants for 0, first, second order. I also put third and fourth just for the sake of, just in case we have an overall reaction order that's third or fourth. But remember that generic equation that we saw in the other, or units for K, will always be 1 minus the total order of the reaction over seconds or over some units of time. The rate constant units do not need to be per second. The time portion can be seconds, minutes, hours, days, and so forth. But 1 minus m plus n. So if it's a 0 order reaction, it would be 1 minus 0, which is just 1 for our molarity, which is why we have a 1 here. If it's a first order, then it would be 1 minus 1, which is 0. That's why molarity doesn't show up here at all. Second order, 1 minus 2 gives us an exponent of minus 1. So molarity to the minus 1, and so on. So that's kind of how that convention works and helps us with determining the units of K. All right, here's our fourth example in this unit for determining the rate law. In this case, we're going to explicitly use an algebraic method. So use the data for the given reaction to determine A, the rate law, B, the order with respect to each reactant and to the overall reaction, and C, the value for the rate constant. And we have this generic reaction where some reactant A produces some products. And we have 3 experiments with initial concentration values for A and a rate in molarity per minute. All right, so we've done this several times now, but just as a reminder, we're going to fill in the general rate law with values from 2 of the experiments, and I've highlighted, I'm going to use experiment 1 and experiment 2. And then, of course, once we have the 2 rate laws, we just divide the larger one by the smaller one, right? So here I've done that. Rate for experiment 2, I'm just substituting the values, 2.69 times 10 to the minus 3 equals K times that concentration, 1.25 to the m power. Divide that by the first experiment, so 1.61 times 10 to the minus 3 equals K times that concentration, 0.075 to the m power. We can simplify this. If I divide these two numbers, I get 1.67. The K's cancel. And if I divide 0.125 by 0.075, I get 1.67 to the m power. Now, this is really straightforward. We don't need that intermediate algebra work with the logs to figure this one out. M in this case has to be 1, right? And so the rate law looks like this. The rate is equal to K times the concentration of A, and then the exponent M is 1, right? That we just determined. But of course, we don't need to write exponents of 1, so we don't see it written there. So here's our rate law for this experiment. Let's look at part B in the next slide. In part B, we're asked to find the order with respect to each reactant and the overall reaction. In part A, we determined that the order with respect to reactant A, that exponent M, was equal to 1. So the order with respect to A is first order. Since A in this case is the only reactant, the order with respect to the overall reaction is also first order. So this reaction is first order with respect to A and first order overall. All right, and then finally, we can use the experimental data and our rate law to find the value for the rate constant. So we start with the rate law that we determined in part A. Rate equals K times concentration of A. I solved for the rate constant, and I can substitute any data that I want from any given experiment. Just to be fun, I chose experiment 3 here. So I substitute the rate, 3.01 times 10 to the minus 3, divide by 0.41, and I've put units here to be very explicit. This is molarity per minute divided by molarity. The molarity units cancel, and just this is a simple computation here, and I get that the rate constant K is 0.0215. This is 1 over minutes, or minutes to the minus 1. And as we saw a few slides back discussing these units, the units of K are often expressed with negative exponents in place of a fraction. So instead of writing 0.0215 per minute, we write 0.0215 minutes to the minus 1. All right, here's a fifth example in this unit of determining rate laws. Again, explicitly using the algebraic method. Use the data for the given reaction to determine the rate law, the order with respect to each reactant and the overall reaction, and the value for the rate constant. So here I have some generic reactant A and B, so two reactants this time that produce some generic products. I've got 3 experiments with initial concentrations of both A and B and the initial rate for the reaction in each case. Okay, so part A, we're going to determine the rate law. So first we got to find the order of the reaction with respect to A. To do that, we're going to use trial 1 and 2, where the concentration of A is changing, but B is constant. Then we'll find the order of the reaction with respect to B, using trials 2 and 3, where A is constant, but B is changing. So let's first look at reactant A with experiments 1 and 2. So I've just substituted for the rate law for experiment 2. 1.74 times 10 to the minus 2 is the rate. We have K 0.217, the concentration of A to the M power, 0.100, the concentration of B to the N power. And I repeat that for experiment 1. 3.70 times 10 to the minus 3 is the rate, equals K times concentration of A, 0.100 to the M power, concentration of B, 0.100 to the N power. These are the same, right? So they cancel. That's why it's important to choose one where that concentration you're not interested in is remaining constant so that it drops from the equation, and so does K. And then we can simplify this. 1.74 times 10 to the minus 2 divided by 3.70 times 10 to the minus 3 is 4.70. And 0.217 divided by 0.100 is 2.7 to the M power. Now, you can go back several slides to the beginning of this section and watch the intermediate algebra explanation for how to solve for this exponent M if you'd like more details. But you can also just guess and check here. If M is 1, then this would have to equal 2.17, so it's not 1. But if I put a 2 here, 2.17 to the second power is 4.70. So the value of M is 1. So here's what we know of our rate law so far. It's equal to K times concentration of A to the second power times concentration of B to some power N that we don't know yet. So now let's use experiments 2 and 3 to find the value of N. So the rate in experiment 3, 1.74 times 10 to the minus 2 equals K times concentration of A, 0.217. Now notice I put a squared here, right? Because I know the value of that M now. Times the concentration of B in experiment 3, 0.250 to the N power. Then for the second trial, 1.74 times 10 to the minus 2 is the rate. K times the concentration of A, 0.217 to the second power, times the concentration of B, 0.100 to the N power. If I divide these two numbers, I get 1, which equals, if I divide, so the K's cancel, the 0.217 squareds cancel. Now 0.250 divided by 0.1 is 2.5 to the N power. Now, what 2.50 raised to what power is equal to 1? Any number raised to the 0 power is equal to 1. So N is equal to 0. Okay? And so our overall rate law is K times concentration of A to the second power. I'm just going to, for the sake of explanation, I'll say concentration of B to the 0 power. But we just got done saying right here, any number raised to the 0 power is equal to 1. So this whole thing will always simplify to 1. And we're always just multiplying by 1. So we don't need to write that. Yeah, so that's why it doesn't show up in the overall rate law. And for our overall rate law, we get K times the concentration of A squared. The rate is equal to K times the concentration of A squared. In part B, we're asked to find the order with respect to each reactant and to the overall reaction. So since M is equal to 2, I'm just going to write the rate law again on this slide so we can be reminded. We had K times concentration of A squared, right? And then just because we're going to use it, it was concentration of B to the 0 power. Of course, we don't write that. I just want to have it here so we can visually explain this. So since M is 2, the order with respect to A is second order. So this 2 means we're talking about a second order reaction. Since N is 0, the order with respect to B is 0 order. The overall order is just the sum of those two things. So 2 plus 0 is 2. So the overall order of the reaction is second order. And again, I just want to remind you, we don't write this in our overall rate law. I'm just showing it here so we can explicitly see the values of M and N. So second order with respect to A, 0 order with respect to B, and second order overall. All right, in part C, we're asked to find the value for the rate constant K. So I take the rate law determined in part A, rate equals K times concentration of A squared, fill in some values from the data. I'm going to just choose trial 1 here. It really doesn't matter. 3.7 times 10 to the minus 3 molarity per second equals K times the concentration of A, 0.100 molar squared. Then just rearrange to solve for K. Right. So 3.70 times 10 to the minus 3rd molarity per second divided by 0.100 molarity squared. So we get 0.370 molarity to the minus 1 seconds to the minus 1. Just check that the units are consistent for second order. We had a summary slide on that a few slides back. Just keep in mind, because this is molarity squared, only one of the molarity units cancels out, and that's why we're left with 1 molarity unit on the bottom of the fraction and seconds on the bottom of the fraction.